Now that we've gotten to a point where we can start talking about equations and inequalities, it's just important to remember that we need to remember the properties that we talked about as far as logarithms and how we can expand things out or how we can actually condense them down. At the same time, when we're talking about exponential equations, just remember that anytime the base of your exponential equations are the same, essentially you can go ahead and take the exponent parts and set them equal to each other. Alright, now we'll get into that a little bit more as we go here. Now essentially there's two different ways we can go about trying to solve some of these exponential equations. And then when we use log equations, it's kind of they hold the opposite effect. We just need to make sure that we understand again how the properties work for all this stuff. So we're going to work on solving both logarithmic equations, inequalities, and also exponential equations and inequalities. Alright, a couple different terms, and you'll get the idea of what these are pretty quick when we start talking about them, but just exponential equations, logarithmic equations. Alright, now we're going to start with the whole exponential equation thing. Alright, now the thing to remember with these is there's really two ways you can go about solving them. This is kind of the main part of the main idea that we're trying to get out of this. Now, if you look over here on the right side, basically what this is saying is if you have two exponential expressions and they're set equal to each other, if the bases of those are the same, I can go ahead and just set the exponent parts equal to each other, kind of like I talked about a little bit earlier. Okay. Now, if you can't get the bases to be the same, all right, our second option would be to go ahead and take the log of both sides and try to use our properties to go ahead and solve that. So we're going to talk about both ways that we can do this. Now, at the end, just like any other type of equation or inequality we've talked about before, you can always go back and check to make sure that your answer actually makes sense. All right. It is important to understand that if you use your calculator to evaluate a log and you get a decimal for an answer, when you go back and fill that into your original equation or inequality, you just need to understand that, particular in the case of an equation, that you might not necessarily get an exact answer because you use decimals. All right, but it should still make sense and it should still be reasonable based on what we just talked about. Okay, now here's our first example. We essentially have two exponential expressions, one on this side, one on this side. They're set equal to each other. Now the whole idea with this is if I can get their bases to be the same, I can go ahead and set their exponent parts equal to each other. Alright, so the first thing I want to look at here is the 9 and the 27, and I want to think about, can I write those more or less in a different form so they would have the same basis? Can I write them as exponential expressions that would have the same base? Well, 9 and 27 can both be written with a base of 3. So technically what I can do is say I have 3 squared, and then I still have the 8 minus x that was originally up there. And that's going to equal 3 to the third, because that gives us 27, plus what's already up above it. Okay? Now, you can go ahead and distribute into those if you want to, but the key here is I've written both of these with the same base. Because their bases are the same, basically what I can do is I can drop the bases and I can just say whatever the exponent parts are can be set equal to one another. And essentially what we're trying to do, just like any other type of equations, we're trying to solve for the variable. Alright, so in this case, I get them down out of the exponent. Now I can go ahead and solve for the variable. So I am going to distribute on both sides. 16 minus 2x is going to be 3x minus 9 from there. Okay, I want to get the x's on one side, the constants on the other side. So I'm actually going to I'll just move my x's left and my constants right. So I'm going to subtract 16, and I'll subtract the 3x over this way. Alright, so when that's all said and done, I'm going to have negative 5x, and that's going to be equal to negative, let's see here, 25. Alright, so from there, it's pretty easy to see if we divide by negative 5, x is going to be equal to 5. Alright, now I can go ahead and fill this in and check just to make sure. So I can go back to my original equation here and say if I fill a 5 in here and a 5 in here, well, that would give me 9 to the third, and that was supposed to be equal to, if I take 5 minus 3, 27 to the second. Now you probably need a calculator to go ahead and try to solve those, or to make sure that they're the same. But if you take 9 and raise it to the third, you get 729. If you take 27 and raise it to the second, you get 729. Alright, so that just goes to show that x equals 5 is the correct answer to this. Alright, now again, there's not going to be a ton of examples on this particular presentation, but what I want you to get out of this is, at the very beginning, like I said, if you can get both sides so you can write the bases the same like I did right here, then these problems become relatively simple. Okay, so I took the 9 and I basically wrote it as 3 squared, and I took the 27 and wrote it as 3 to the third, and I left those other aspects of the exponent there, and then I can go ahead and take everything and set it equal to each other without the bases there anymore. Okay, now this is a little bit different, and this is kind of your other approach to solving exponential equations. In this case, you'll notice, technically, remember, if I just have a 5, technically it's 5 to the first, but we don't have to write that up there. What's a little bit different about these is, if you look at it, the bases would be 4 and 5. Alright? You can think to yourself, is there any way that I can write those so that they would be different numbers but have the same basis? You know, like we did in the last one, 3 to the second, 3 to the third. Well, it's not going to work this time around, so I have to explore my other option here, which would be, I'm going to go ahead and just take the log of both sides, common log. So log of 4 to the x minus 1, and I'm going to take the log of 5. Okay, now initially it doesn't really look like it does a whole lot for us, but I'll explain what's going to happen here. And essentially what we're looking at is, I'm going to use my properties of logs, and eventually I'm going to end up with a decimal as an answer, but I can still evaluate things this way. Alright, now ideally, like I said, if we could have got the bases on both sides to match up, it becomes a much easier problem. It's going to have a much simpler answer. But in this case, what I want to do first is I want to focus on this side. Alright, and I'm going to use my exponent or power property. So I'm going to take that x minus 1 and I'm going to write it out front. And I'm still going to have log 4 right there. So I'll just put it in parentheses so we know it's separate. On the other side, I'm still going to have log of 5. Okay, now what I want to do with this is, remember, log 4 and log 5 are basically just numbers. Alright, and if I don't see bases written there, it just means they're base 10, which is going to help me out here in a second, because the only way that's actually going to help me to evaluate this is if I can use my calculator. And remember, you can only use your calculator if you have log base 10s, or if you want to use a change of base formula, but it's much simpler if we just think log base 10. Okay, so what I'm going to do here is I got to get the x by itself, so I'm going to divide this side by log of 4, because just remember, log of 4 is really just a number. Okay, so that's going to leave me with x minus 1 equals log of 5 over log of 4, and then my last step would be I have to add the 1. Okay, so x is going to equal log of 5 divided by log of 4, and then I'm going to add 1 to it. Okay, now that right there is your technical answer. Technically, if you want to be exact, you would just leave it like that, because when you put log 5 divided by log 4 in your calculator, you're going to get a decimal. Alright, but we're going to go ahead and we're going to simplify, and we're going to try to find a decimal answer. So with your calculator, you're just going to take log of 5, and you're going to divide it by log of 4. You're going to get a decimal answer that's roughly 1.16. Okay, and then we're going to add that 1 to it, so we're going to get roughly 2.16. Alright, so x equals 2.16 would be my answer to this. Now, this is what I talked about from the very beginning. If you were to fill 2.16 in, and you're trying to check to see whether that works, and we can go ahead and do that, I would fill the 2.16 in up here. So essentially 2.16 minus 1 is going to be 1.16. So if I take 4 and raise it to the 1.16, I get roughly 4.993. Okay, well, it's not exactly 5 like it says it should equal on the other side over here, but it's close enough, and you have to understand, because we decided to make this part a decimal, that's probably about as close as you're going to get when it comes to checking. Okay, now the important thing here, remember, is, it might seem kind of weird at the beginning where we just go ahead and take the log of both sides. Just remember, you can do whatever you want to to either side of your equation as long as you do the same thing to both sides. Okay, so we took log base 10 because that's going to make things easier when we use our calculator. But technically, you could take a log to any base of both sides as long as you do the same thing to both sides. In this case, because there's not much in common with the 4 and the 5, it really wouldn't make any sense to use a different base other than 10, because ultimately you're going to have to use your calculator anyway to go ahead and find an answer. Alright, now, story problem. Again, you're pretty much looking at doing the same thing that we did before. The only difference is you have to come up with the equation that we're talking about here. So it says suppose a bacteria culture doubles in size every hour. How many hours will it take for the number of bacteria to exceed 1 million? Well, essentially what you're looking at is every hour it's going to double. So I'm going to just write something that looks like this. Okay, so what that means is obviously if you start with 1, that's fine, but we put 2 as our base because if n is supposed to represent the number of hours, alright, well after the first hour you'd have 2, after the second hour you'd have 4, after the third hour you'd have 8, so on and so forth. So it's doubling every hour, taking the number in front of it and going from there. Okay, now if we want to figure out how many, or basically what n is supposed to be, alright, we're going to take a similar approach to what we did on the last problem. Okay, or we could, use the first problem. If you could figure out, can I take 2, because my base over here is 2. If I could write 1 million as 2 to some power, that would be the easiest way to do it, but that's probably going to be a lot of guessing and checking. So what we're going to do here is we're just going to do what we did on the last one. Log of 2 to the n equals log of 1 million. Okay, we use our exponent properties, so pull the power out front. So n times the log of 2 equals the log of 1 million. Okay, and from there we just divide by the log of 2. So again, it becomes a calculator problem. N is going to equal whatever log of 1 million is divided by log of 2. So log of 1 million divided by log of 2 is going to give you roughly 19.93. Okay, oops, 19.93. Okay, now it's one of those things again. It's not necessarily an exact hour amount, but that's as close as we can get because we're filling this in. And essentially what that probably means is it's not necessarily going to meet 1 million right on a given hour amount. Now the other thing to keep in mind, and I probably should have mentioned this from the beginning, is it does say when is it going to exceed 1 million. So technically what we probably should have done is we probably should have said if this is going to exceed 1 million, technically at the end here you probably could have used a greater than sign. N would have to be greater than 19.93 in order to exceed 1 million. So instead of using the equal sign at the beginning, I probably could have used an inequality sign, where n again has to be greater than 19.93 for us to exceed 1 million, because right at 19.93 is going to equal pretty much right at 1 million. So that's where the whole inequality aspect of this whole thing comes into play. Alright, so if it had said equal, we could have left an equal sign right in here. Alright, but because it says exceed, we probably have to approach like it's an inequality. Alright, now the other thing that we're going to talk about here is just what you do with logarithmic equations. Okay, and this again is really not difficult. The exponential ones I think are probably a little bit easier, but this will make quite a bit of sense when you go ahead and try to solve this. And basically what you're trying to do is you're just trying to figure out how to solve for the variable that's in a log problem. All right, and what you're going to need to be able to solve for these is you're going to have to remember all those properties of logs that we used in lesson 7.4 when we were expanding and condensing things. And actually in this case, condensing or writing things as one logarithmic expression is going to be the most helpful in doing this. So now what we're going to look at is something like this. Okay, what you need to remember is, again, your properties from section 4 is if we were able to have an exponential expression that had a log as its exponent, if the bases of both of those were the same, things became a lot easier. So what I'm going to do is, it's referred to as exponentiating. I'm actually going to do this, and I'm basically going to say I'm going to rewrite it as 6 to the log 6 of 2x minus 1, and then 6 to the negative 1 on the other side. Alright, so again, it's kind of like when we took the logs of both sides when we were doing exponential equations. What I'm going to do here is I'm actually going to turn this into an exponential equation. Alright, by exponentiating both sides. And the whole key is, if I make the base down here the same as the base up there, this becomes a lot easier because I know the answer to that is just going to be 2x minus 1. Okay, and that comes from our property stuff. And that's going to equal 6 to the negative 1, which is essentially 1/6. Alright, so to solve this, I'm going to go ahead and add 1. So 2x, and if you want to just say it's 1 and 1/6 for right now, that's fine. Okay, and I'm going to go ahead and divide by 2. Divide by 2. Alright, so x equals, now think about this, if you divide by 2, it's the same as multiplying by 1/2. Now what I probably should do is I should take this top part and write it as an improper fraction. So that would be 7 over 6 times 1/2. Instead of dividing by 2 again, I'm going to multiply by 1/2. Alright, so you get 7 over 12. Alright, so x is going to equal 7 over 12. Alright, now the key here is I would very much prefer that you try to keep things in terms of fractions as much as possible, as opposed to giving me a decimal answer here. The reason for that is fractions are your exact answers. Decimals are always approximations. Alright, so if we want to make sure that we're staying as specific as possible, we need to make sure that this part remains fractions, and so does our answer. Okay, now here's another example. What you'll notice with this one is it's a little bit different. We have a different base, and you'll also notice that we have two different log terms on the left side. Now before you can exponentiate something, and this is very important, is you need to make sure that you condense things or simplify them down to where you only have one log expression in the entire equation before you exponentiate. So what I need to do is take this stuff right here and use my properties that involve subtraction and division to go ahead and write this as one log. So what it's going to end up being is log base 4 of 100 over x plus 1 is going to be equal to 1. Okay, now again, all that does is that just comes from the properties we talked about in section 4. But now, once I have it written as one log, now I can exponentiate, and I'm going to want to use 4 as my base. So I'm going to say 4 and 4. So essentially 4 to the log base 4 of 100 divided by x plus 1 equals 4 to the first. Alright, again, basically this stuff cancels each other out. So I have 100 over x plus 1 equals 4. 4 to the first is 1. Okay, now to solve for this, and this might be a little bit more of a lengthy process, I have to get it out of the denominator. So I'm actually going to multiply both sides times x plus 1. Alright, well that'll cancel it off over here and move it to the other side. Alright, so I end up with 100 equal to 4x plus 4 after I distribute. Okay, now I want to subtract my constant. I'm going to move over here to the right. So essentially I end up with 96 equals 4x. Alright, so to figure out what x is, I would divide by 4. Okay, now 96 divided by 4 gives me, 96 divided by 4 gives me 24. So x is going to equal 24. Alright, so technically that's my answer here. Now you just want to make sure that your answer makes sense here when you go back in. So if I were to fill 24 in here, I would get 25 log base 4 of 25 minus log base 4 of 100. Okay, I just want to make sure that that makes sense. So it's all said and done, essentially you're going to get log base 4 of 4 after you throw your properties in there. But sometimes you just need to make sure that number you get for your answer makes sense when you fill it back into the original, because there are going to be times, we've seen this with other types of equations before, where when you fill your answer back in and it doesn't make sense or it doesn't actually equal out. So you just need to be aware of that. Okay, and that's really what this next slide is pretty much telling you. Watch out for calculated solutions that are not actually solutions of the original equation. So it's one of those where you probably want to make sure you check after you're done and go back in and make sure that it actually makes sense and works. Because there will be instances where it doesn't, and if you list that answer when it doesn't actually work when you fill it back in, technically your problem is wrong. All right, now the last thing here, and I'm just going to talk about this real quick, is using a calculator to figure out how an inequality or even not an inequation, but how an inequality or an equation actually works if you want to use your graphing calculator. So in this case here, if you end up with something that looks like this, you have an equation, actually it's an inequality, but an equation would work in the same way, where you have variables on both sides, and your best bet would be to try to use a calculator to solve it. Basically what you do is you graph this in your y1, and you would graph this part in your y2. Okay, so you graph them and basically end up with two graphs on your window. Okay, what you're looking for is the point at which they intersect. The point at which they intersect would be the point at which they're equal. Okay, so whatever your x value is where they intersect would be basically the answer to the equation, or where they're equal to each other. So in this case here, where x equals 16, all right, these two graphs would be equal to each other. Now in this case, because it started out as an inequality and we want to know where the first line, okay, which would be this one down here coming up, is greater than the second line, which is just a linear equation going this way. All right, because we want to know where the first one is greater than the second, technically our answer isn't x equals 16. It's going to be x is anything greater than 16, because once we get up here, my exponential part is above my linear part. Okay, so what that means is as our x values go this way, as x gets bigger, this graph is greater than this graph. So that's what I'm looking at here. So x being greater than 16 would actually be your answer to this. Okay, and again, if you're just looking at it this way, again, if you look at your table, what you're looking at is where is this part greater than this part. So if this is your first equation, the exponential part, and this is your second equation, at what point do the values on this side become bigger than the values on this side? Okay, that would be your basis for how you would write the range of numbers that could be an answer to this. All right, now this is pretty short, straightforward, and to the point. You just need to make sure that you understand, all right, the different methods that can be used to solve both exponential equations and inequalities and logarithmic equations and inequalities. All right, with exponential, there's two methods you can use. You can either log both sides and use logarithmic properties to simplify your answer, or you can work to the point where you have the same base on both sides of your equal sign, and then you can go ahead and set the exponents equal to each other and solve. Best case scenario would be to use that route. Okay. When it comes to logarithmic equations, you're going to have to do something called exponentiating, okay, or basically where you figure out what base would help you the most, which is going to help eliminate what's going on there, eliminate one of your log functions, and then you can solve from there. The important thing to remember with exponentiating is you cannot do it until you only have one log expression as a part of your equation. All right, so you need to condense all your logs as much as possible and get them on one side of the equation, right, before you decide to exponentiate things. Okay, so that is pretty much kind of in a nutshell what we're looking for in this particular section. All right, hopefully that gives you enough to get started on your assignment. If you have questions, just make sure you ask.